Okay, welcome everyone. I think we'll start. So, good evening. This is NOC 25EE110 NPTEL tutorial session on microelectronics devices to circuits. The course instructor is Professor Sudeb Dasgupta from IIT Roorkee. I am Debashish from IIT Kanpur. So, I am one of the TA assigned to this course. So, we go live every Saturday 7 to 9. So, this is week 8. I think let's begin. So please confirm someone that if can see the screen and I am audible.
Yes, sir, you are audible and the screen is visible.
Okay, fine. So the first part of today's session, we will do some basics of the inverter sizing and more importantly, logic gate sizing. And then we will proceed to some of the analog circuits applications. Okay. So how do we solve this problem? Logical effort of a 3-input NAND gate is, and your mobility ratio is given. How do we solve this? So what do you mean by what is CMOS logic? Anyone?
It's a combination of PMOS and NMOS circuits.
So what is the full form?
Complementary mix.
Complementary MOS logic. So what are the key features of this kind of circuits? So we will have the topology will be something like this. So this is your power supply rail, this is your ground, and there will be multiple inputs. Okay, we call it PUN, we call it PDN, and from this node, we will have our output, and that output will be basically connected to some load capacitance. So this will be your V out in terms of voltages. Okay. So can you tell me what is PUN and PDN? Anyone? So I am trying to go through a formal analysis of the CMOS logic, okay? So that if I do it for in general case, so it will not only be for NAND gates, you can design any gates for that matter. So what is PUN?
Pull-up network.
So why it is called pull-up network?
Because if this network is active, my output is connected to VDD. So it's
No. What is pulling up then? What do you mean by pull up something?
pulling up means the increasing the voltage level.
Which voltage level?
The output voltage.
Yes. So what is pulling up means I am increasing V out from 0 to VDD, and pulling down means I am discharging the CL basically, right? V out will be pulling down from VDD to 0. So that is how the name came about. So now can you tell me, to have pulling up of the output voltage, what network should be active and what network should be passive? Means what network should be on and what network should be off? Basically,
Pulling up the output.
yeah.
PUN should be active.
So
PDN
right. So when PUN is active, my PDN should be
inactive.
inactive, right? So one of the main constraint is that only PUN or PDN will be active at a single time instant, right? So that we should remember. Now the question is, the question would be, how do we design PUN and PDN? Basically, the question what I wanted to ask is that what should I use in my PUN and what should I use in my PDN? For example, let's talk about PUN. And the simplest CMOS logic, you know, what is the simplest CMOS logic, you know?
Inverter.
The inverter. Okay. So now let us consider PUN is comprising of either one PMOS or one NMOS. So what should I connect in, what should I use in case of my PUN, PMOS or NMOS?
PMOS.
Why do I do so? For example, let's say this is your PMOS, right? And it will be my CL. This is your V out. This is your V in. Another case that can be is this. This is my CL. This is my NMOS. So why do I use the first one and not the second one? Can you tell me? You have to understand these things, right? Simply by knowing the things does not serve any purpose. So tell me what will happen if I use my PMOS?
I can get the entire swing from 0 to VDD in the case of
So what do I mean by swing? So voltage swing. Voltage swing is basically your V out range that it can travel. What is the range that I want? I want from 0 to VDD, right?
yes, sir.
Now, for example, in case of PMOS, this is my gate, this is my source, this is my drain. And in case of NMOS, this is my gate, this is my source, this is my drain, right? So in case of when my PUN is active, then I should have both the transistors on or the transistors in the PUN network on, right? So that I can have a path between VDD to V out. So to on the PMOS transistor, I generally use 0, and to on the NMOS transistor, I use VDD. Fine.
Yes, sir.
So what is the condition? So now what is the condition for PMOS to be on? PMOS will be on when my VSG is greater than VTP, right? And my NMOS will be on when VGS is greater than VTN, the threshold voltage, right?
Yes, sir.
So now what is my VGS in this case? What is VGS? VGS is nothing but your VDD minus 0, right? And what is my VGS in this case? That is VDD minus
V out.
V out. So VDD minus V out greater than VTN. Fine. Now what is changing? My this quantity is changing, right? I want this to go from 0 to VDD. In this case, my PMOS will always be on, right? Because I have my VGS equal to VDD and that will always be greater than your VTP. Fine. This potential difference. But in case of NMOS, so let me take one point. Let's say there is a point that is my VDD minus VTN. So for PMOS, for NMOS, my VTN is a positive quantity, generally true for the modern technologies. So this quantity will obviously be lesser than VDD. Fine. Now tell me what will happen if my output is in this region. If my output V out is between these two region, then what is my VGS of NMOS? That will be my VDD minus some voltage greater than VDD minus VTN, right?
Yes, sir.
And what will that make?
Transistor off.
So this quantity will be less than your VTN. So that will essentially make my NMOS in the off state in this region. Let's say this is region 1, in region 1. So if my NMOS is off, that means my this path is not active anymore. That means my capacitor will not get charged further than this voltage. So if I use NMOS in my PUN network, so if NMOS is used in PUN, so what is the voltage swing I am getting from 0 to VDD minus VTN, right? So I am not getting the entire range. Now let's say your VDD is 1 volt and your VTN is in 0.5 volt. For example, let's say. So your output voltage is getting maximum till 0.5. So it is around that switching threshold of that CMOS inverter. So you cannot determine that whether your output will be, from looking at the output, you cannot determine whether your input is 1 or 0, right? So that does not serve any purpose. So that is why voltage swing at the output node is important. And we use generally this in case of PUN network. With the similar argument, you can show if we use PMOS in PDN, we will not get the entire swing. And what will be the issue? And what do I mean by output swing in this case? Output swing, ideally, I want VDD to 0 in case of my discharging of the capacitor. When CL discharges. But if I use PMOS, I will get my output till VTP. Okay, you can check this. So that is why we use. So what is the conclusion? PUN comprising of PMOS network and PDN comprising of NMOS network. If that is true, then let us try to design some logic gates. So tell me one thing, what are the universal logic gates?
NAND and NOR.
And why do you say so?
Because with these two gates we can basically make any basic gates.
With these two, I can make the entire set of basic gates. Okay, so that is why I will design the NAND and NOR gates. Fine. So let us design 2-input NAND gate and 2-input NOR gate parallelly. So what are the truth tables of NAND and NOR gate? So let's say,
Sorry,
yeah,
e- NAND and NOR gate AB plus Y, sir. No, sir.
AB,
AB and Y, sir.
what is the last term you are using? So you mean to say this one?
Yes, sir. Yes, sir.
So I will have AB in this case as well as AB in this case. So this is my PDN, this is my PUN. So I want to design my PDN and PUN. Okay. So what is my AB and let's say F? So I can have 4 combinations. So in all these 3 cases, I want 1 and this case I want 0. Right? So how do you start with designing any gates? Let's say you do not know, you have some complicated kind of stuff. Then how do you start designing those things? First step is you take PDN. Okay. Now you have 2 inputs, right? That means you have two inputs will be provided at which points? Inputs will be provided at the gate of the transistors, right? And why it is so? So I think you should discuss this thing. So can you tell me one thing? So nor I'll do later. So can you tell me one thing? 2 inputs means 2 transistors, minimum 2 transistors at PDN and PUN. How can you say that? The question is, if I have two inputs, I need to have at least two transistors in my PDN or in my PUN. Why am I able to say that?
Because my logic is of two logic levels, 0 and 1. So in order to work one of them, I need one of the transistor to be on.
So the concept is that you want either on or off, right?
Yes, sir.
That means what?
One of my transistor will be active and one will be deactive. And
No. That means you are applying your input at the gate terminal of the device. So basically what you are doing, so let's say you have a signal at this point, right? You want that signal to pass through the transistor and come at this point in one case. In other case, it will not pass and I will get 0. That means I am having some switching kind of action, right? So by applying these inputs or A or B, I need to switch on and off my transistors. That means I need to apply the inputs at the gates of the transistors. Input has to be provided to the gate of the transistors. Okay. So that is why I need at least one gate for one input or one transistor for one input. Now let me tell you something. So you are aware of this kind of MOSFETs, right? This kind of MOSFET structure you are aware of?
yes, sir.
So this kind of structures are basically called your bulk MOSFETs or your conventional MOSFETs. Okay. Now I am showing you something different now. So this is your FG, this is your BG, this is your source, this is your drain. So can you tell me what is this structure? So basically this is your oxide and this is also your oxide. This kind of MOSFETs are called SOI MOSFETs, okay? Or your silicon on insulator. SOI stands for silicon on insulator. So basically this is your silicon, this is your insulator. So in this case we do not have a bottom insulator, right? Bottom oxide. So that is why this kind of structures are called silicon on insulators. Now can you tell me how many gates are there in this?
Sir, two, sir.
Exactly.
Two.
So there are logics. If I have to make two input gates or logic gates. So from now on, to determine the gate of the transistor, I will use this symbol, and to mention logic gates, I'll write the entire thing gate. Okay. So two gates. So I have to make two input. I have to make a logic gate with two inputs. One transistor is enough. Okay.
Yes, sir.
Because I can turn on and off. So what am I actually doing? I am just turning on this channel or turning off, right? So in the second case, I can use two gates to turn on and off the transistor. So I can get four combinations out of it, right? So one transistor will be sufficient for me to design the gates. So remember this thing. It is not always true that minimum two transistors are required for two input gates. That is true only if your MOSFET is a bulk MOSFET or the conventional MOSFETs that we are designing. Okay. So if these kind of tricky questions are getting asked, you are asked, so you will be able to answer. Fine. So now designing the PDN. So let's say I have two transistors. First thing, PDN will be made up of NMOS. So how can I connect these transistors? I can connect it in this fashion. So this will be my CL and this is my V out or F. This is, let's say, A, B, or another combination I can have it in series. Fine. So the upper part I have not drawn. So there will be, because this will be open circuited anyhow when my PDN is activated. So can you write the truth table of this for this guy, let's say ABF, and in this case ABF. Let's do this one first. So what will be the logic? If my both transistor inputs are 0, 0, then what is the status of the MOSFETs? Both will be on or off?
Off.
So what will be my F?
0.
Why 0?
If the voltage level it is at, so
It will have the previous value, right? Whatever
yes,
is happening at this node, let's say earlier it was 0, so it will have 0. If earlier it is 1, it will be 1. So what do you expect your pull down network? When do you expect your pull down network to get activated? When the output is 1 or when the output is 0?
1.
You want to pull that 1 down to 0, right?
Yes.
So you want your previous stage to be 1. Similarly, 0, 1, what will be the case? In case of 0, 1,
0
so
is connected to ground.
A will be off,
In
but B will be on.
yes,
So I have a path, right? Still,
yes,
it is in parallel. So what will be my output?
0.
Similarly, this will be 0, this will be 0. Fine.
Yes, yes.
Now, what about this case? When both transistors are off, obviously I will have it connected to previous stage. Right?
Yes, sir.
And what about if one is on and other one is off?
Still, it will be previous stage because it cannot flow to the ground.
Yes. So the circuit is not closed, right? The capacitor cannot discharge. If this is on and this is off, it is equivalent to the entire thing is off because it is in series connection. So in this case also it will hold previous value. This case also it will hold previous value, and when only both are on, then
It will
only it will go to 0. Now can you see and tell that what is the which one should I use for NAND gate?
the lower one. Okay.
So the bottom one is the preferable one, right? Similarly, if you design your pull-up network, so I can have I need to have two transistors, so I'll have, let's say, VDD. So this is my CL, this is my F, and this is my A, this is my B. Similarly, I can have them in series. VDD, A and B. So quickly tell me the truth table for this. 0,
Sir,
0, 0. Yeah,
0, 0, 0, 1, 1, 0, 1, 1, sir. Sir, it is
yeah.
0 no, sir. It is 0 no, sir. F in place AB is equal to 0 no, sir.
Sorry.
Sir, in you have A in place 0 no, sir. You have done your right. You have written 0 no, sir, in place of A.
In which case? This one? So tell me what will be this case? When A equal to 0, B equal to 0, what should be my F?
0.
Why? It is PMOS, right? 0 will turn
Yes, sir.
on the transistor.
Sorry, sir. Sorry, sir. It is on
It is 1, right?
Only for one it will be 0.
1.
Rest for case it will be
Only for 1 it will hold the previous stage
previous.
Okay.
because it is a capacitor, right?
Yes,
I
sir.
have not mentioned you what is the previous stage. Mostly it will be 0 because we want to pull up it.
Sir,
And
can we
what about,
write? Sir, can we write it in 0? We can write previous. No, sir. In F, we can write previous bracket 0. Like that, we can write no, sir, in NAND gate.
so I'll come to that. Why I am doing that, there is a particular reason. Okay.
Okay, sir.
So in this case, what will be the scenario? Only in case of 0, 0, you will have 1.
It will be 1.
In other cases, you will have
It will
the
be
previous
previous.
stage.
Yes.
So what do I mean by previous stage? Previous stage means then previous stage means my pull up, in this case, my pull down network is off, right? These are the cases when my pull down network is off. And these are the cases when my pull up network is off. Do you agree with that statement?
Yes.
And what about in these cases, my pull up or pull down networks are conducting. So can you see from these tables that whenever my pull up network is on, for example, let's say, oh, by the way, for two input NAND gate, what should I consider? So this is my truth table of the NAND gate, right? So I should consider this one for two input NAND gate. So now how do I connect my 2-input NAND gate? This will be my pull-up network, and this will be my pull-down network. Is it okay? This is my 2-input NAND operation. Now for 2-input NAND operation, if I consider this one and this one, can you see that whenever my pull up network is active, means these three cases, then my pull down network has to be off. Similarly, whenever my pull down network is active, my pull up network has to be off. Is that okay? So we have verified our this statement. Right?
Yes, sir.
So another way how you can see, let me just copy this. So let us take this case 0 0, and we want to find out what is f. This is a equal to 0, b equal to 1, f equal to, we'll find out. This is a equal to 1, b equal to 0, f equal to, we want to find out. And this is a equal to 1, b equal to 1, f equal to what? So just by looking at it, when my both 0 0 are activated, so I have these paths connected. Right? You can see a direct path from VDD to F. So what will be my output? Output will be 1. Similarly, in this case, A is 0. So my A path is connected to the output. B is 1. That means B is off. In this case, my B is on. Right? So in this case also, I will have F is 1. Similarly, in the other case, I have this path activated and this one activated. But as that is in series, so this will also give me 1. And in this case, I have both 1. That means this will be deactivated, and I have the entire path from F to ground. So if this is deactivated, in this case also this is deactivated, in this case also this is deactivated, and in this case this is deactivated. Do you see how the NAND operation is happening?
Yes, sir.
Okay. So far we have seen how we have connected the NAND, how we have designed the NAND gate. So I hope you will be able to. So what you will do, design similarly for 2-input NOR gate. Fine. And what about other gates? Minimize expression using K-map. You know about K-map or Karno map?
Yes.
Gate in terms of sum of products or products of sum. From this you can, so this is basically your AND, OR and NOT operation, right? So you will have your AND, NOT and OR operations and design these gates using your NOR and NAND. And even in sometimes if the circuit is if the logic is very simple, you can directly implement it using AND or NAND or NOR operations. Okay. So far that is fine. Now we will move into the sizing of the transistors. So we will now do sizing of 2-input NAND gate. So what are the constraints? So let me first. So what does this symbol means? This one, what does this mean?
The combination of many lines.
So this means multiple bits, okay? Multiple inputs. So in digital circuits, this means single bit. This means multiple bits or multiple inputs, okay? So this is a simple way to represent multiple lines. Okay. So my PUN network is comprising of PMOS and this is comprising of NMOS. So what do we want? We want to have symmetric delays. What do I mean by that? What do I mean by symmetric delay?
TPHL equals to TPLH.
So TPHL is equal to TPLH. So what does TPHL will look like? So what will be this?
N.
TPHL.
Sorry. Yes, N. It will be N, and for LH it will
So
be
N in this case, we will write it as PDN. It will be PUN, right?
yes.
And let us consider inverters. So remember always that digital circuit design or VLSI design all about simplifying things. Okay, we do not want anything complicated. Fine. So if that is so, can you tell me if this is proportional to WP by LP times mu P, proportional to WN by LN times mu N? Is that okay? I think this we have discussed in last session.
Yes, sir.
So WP by LP divide by WN by LN. This is of PUN. This is of PDN. Should be equal to mu N by mu P. Fine. So that means if mu N is equal to K times that of mu P. So I have to make my PMOS transistors K times that of W N of Ln. Fine. This is the first condition of sizing of the CMOS logic. That means I want to make, I will consider this as 1 and then I will have the size of this as K. Okay.
Yes.
This is condition number 1. So we consider condition number 2 is worst case delay. So what do I mean by worst case delay from this formula? Worst case delay means TP highest or TP lowest?
Highest.
So I will check always for the path where my TP is highest or the case where my TP is highest. And for TP to be highest, what should I consider? My R-on should be, I will check that combination where my R-on is highest. We will always check for that combination. I will tell about what do I mean by combination. For check for that combination where R-on is maximum or R-on is highest. Fine. Now let us try to get the delay of 2-input NAND gate. So let me just copy this. So I want what? Let's say this is my PDN, right? And let's say this is my PUN. So what will be the size of PDN? Let's say PDN size is 1. So what will be the size of PUN? PUN size will be K, right? From this is coming from this factor. Now can you tell me, if I write this as 2, does it make sense to you?
Yes, sir.
Others? So basically what is happening, you have two resistances in series, right? And resistance is inversely proportional to your W by L. So basically you will have one R on and another R on. So your W by P, it is inversely proportional to W by P. Sorry, W by L. So to get the overall thing 1, what I will do, I will make these two half, right? I will just add this one, this half and this half gets added, and half means your W by L has to be multiplied by 2. This is what I mean by making it 2. And what about this PMOS? What is the worst case? What is the worst combination? In case of PMOS, I can have, this is my VDD, I can have this, or I can have this. So what do you think will give me the worst resistance? Case 1 or case 2?
Writing case
Yes.
2, sir.
Case 2, right? Because in
Yes,
case
sir.
1, when I am having this combination, I have 2 paths. So my delay is basically effectively getting half. But in case of this case or this case, which are the worst cases, that will give me the highest amount of resistance. So again, I have told you that I could design, or we could design it considering both the cases. But in case of VLSI designs, we want things to be simpler. So we will go with the worst case thing. If my worst case is covered, my design is such that my worst case is covered, then other things, best case will also get covered, right? So thinking in that line, so can you tell me what will be the sizing of this and this? I will have the same size in both cases, right? Is it understood?
Sir, can you explain once more, sir?
Yeah. So what is happening? I want my PUN network on resistance to be K. Fine.
Yes, sir. Okay, sir.
So I will assure that my K resistance to be in the worst case path. So let me give you another example. For example, okay, so let me give you the example for uh, 2 input NOR. So what will be the NOR gate NOR gate? How will the NOR gate look like? It will look something like this. So this is my NOR gate, okay? 2 input NOR gate. So again, what I'll check, this is my PDN, this is my PUN. So I will have overall size 1 here, fine, and I need to have overall size K here. Is that much clear? This is coming from the mobility condition. Is that much clear?
Yes, sir. Yes, sir.
So what is the worst case in case of PDN? When one transistor is active or 2 transistors are active in parallel?
One transistor active in parallel.
When one transistor is active, right? So I
Yes,
will
sir.
just simply size the transistor as 1 1. Whereas in this case, I was sizing the transistor as 2 2, because then my worst case is the case when both transistors are on, right?
Oh, yes, sir.
So in this case, I will size my transistor in such a way that my both one transistor is on, and that should give me the overall delay of the PDN or pull down network. Similarly, can you just tell me what should be the sizing of this PMOS? What is the worst case here? When both PMOS are on or both PMOS are off? Sorry, when both PMOS are on or one PMOS are on?
One PMOS on, sir.
Why? One PMOS, when one PMOS is on, then there will be open circuit, right? So
Yes, sir.
So let's say even if there is no open circuit, so there is one case this, another case this in series case. Which is the worst case? Which is the worst case or maximum resistance?
Second one.
Second one.
This one, right?
Yes, sir. Yes, sir.
So I will size it as twice K and twice K to convert the overall delay of the PUN network so that it becomes K. Is this clear?
Clear, sir.
So if that is clear to you, now we will come to the question. 3 input NAND gate with mu n by mu p equal to k equal to 3. So first thing is we will draw the 3 input NAND gate. So can you tell me what should be the sizing? Again, first thing what you will do, what is the overall size should be? What the overall size should be
Of PDN.
of PDN?
So 1.
Of
It is always 1. So what is the size of the PUN?
3.
3, sir.
And why this 3 is coming from? It is coming from this.
Yes.
PN by PUP.
So what should be the individual transistor size for this case? Ankit, you don't answer. Let Surya Satvik answer. Yes, Surya, can you tell me what should be the size of A, B, and C transistors? You are on mute. You can give wrong answer. There is no harm. Can you please unmute and tell me what should be the size of A, B, and C transistors in case of PDN? Yes, Surya Satvik.
Yes, sir. Yes, sir.
So what should be the size of ABC?
Sorry, in PN, sir.
In this case, PDN. So think in terms of worst case delay. When will the worst case delay be? This is in series, right?
Yes, sir. It is in series, sir.
So when will the worst case be? We have just discussed above, right? So the worst case will be what? When this entire thing is conducting, right?
Sir, it is
That
conducting all. It's conducting around the series, no, sir.
yes. So the worst case delay that depends on the highest resistance in series will be dependent on when all of the transistors are on. So when all
When
of the transistors are on, these three transistors, right?
yes, sir. ABC is
All are on.
all
That
are on, sir.
means A, B, C equal to 1, 1, 1 condition will be the worst case for the
Yes, sir.
pull down network.
Pull down network.
So
Pull down.
how should I size my ABC if my overall thing
Sir,
has to be 1?
overall, we can size it on 0, 0, A is equal to 0, B is equal to 0, and C is equal to 1, no, sir. Then we can change equations, no, sir.
If A equal to 0, then this path is not at all conducting, right?
Yes, sir.
So I want to consider, so my worst case will be what? These three resistances. So let's say this is R1, this is R2, this is R3, right?
Yes,
Corresponding to this. So overall this should give me, so R1 plus R2 plus R3 should correspond to W by L equal to 1 of the overall thing, right? Do you understand this much?
yes, yes, sir. Yes, sir. Understood.
So what should be the W1 by L1 and W2 by L2 and W3 by L3? So these all are same. So what should be this?
W by L1 is equal A, no, sorry. W by L2 is B.
Yes. So this is your, let me clarify this point further. So we are considering this network, okay? So I have here F connected and all three transistors are conducting. This much clear?
Yes, sir. Clear, sir.
So R on A, R on B, R on C. Fine. And let's say all are same, R on. So your 3 R on has to be equal to R on of pull down network. Fine.
Yes, fine. Yes, sir.
So let's say this is R on of pull down network. Now I want to find out what are the transistor size of this. So what is R on? R on will be some proportional to 1 over what? W by L
W by
of the NMOSes, that has to
yes,
be
sir.
equal to something proportional to 1 over
W by L.
W by L of the PDN.
Yes, sir.
Is that clear? Is this much clear?
Yes, sir. Clear, sir.
So now let us remove the proportionality constant because the transistors are same NMOS, so that will be same. So can you just check that W by L NMOS will be 3 times of W by L of PDN. So if I have this as 1, so these individual transistors W by L should be 3. Because this is 1, right?
Yes, sir. It is 1 of the W by L into 3 into 1 of sir. Let A be A is
So,
equal to 3 and B.
so individual transistors W by L will be 3.
Yes, sir. Yes, sir.
So you should be able to tell it directly by looking at the architecture of the CMOS logic. Okay.
Sir, little bit confusion, sir. I have forgotten the
Yes.
formula and
No,
forgotten the formula.
there is nothing to forget about. There is nothing to remember for that matter. So understand this much. Your I
A
is
little
1.
bit confusing, sir.
No, this you understand. This you remember, right?
Yes, sir. It is. Yes, sir.
If this you remember, so what will be your R on? R on will be DID by
DID by
dVds.
DVD.
So
DVD.
that is proportion. So R on inverse is that. So this is basically your, let's say, G on or 1 over R on. So this will be proportional to W by L. So your R on will be inversely proportional to W by L. Or in other way, you can remember this. So if your W by L is increasing, current increases.
Yes, sir.
So your R on will decrease. Right?
Yes, sir.
So you should remember that R on is inversely proportional to W by L. You should understand that. So from that logic, if your PDN W by L is 1, so you can immediately tell your transistor W by L. Okay?
Okay.
Now can you tell me what should be this? Your PUN W by L is 3 by 2. Can you tell? Ankit, can you tell?
So it would be 3. All
Each
3.
of each of them will be 3, right? Because the
Yes.
worst case path is the single transistor. So it will match the PUN network.
Yes.
Okay. So this is how you size your logic CMOS logic gates. Now the question is, if that is so, and what about CMOS inverter with mu n by mu p is equal to 3? How do we size that? Quickly tell.
It is 3 now, sir.
So,
PDN is 1
TDS.
and PUN is 3.
right?
Yes, sir.
So now we will define something called logical effort.
Excuse me, sir.
Yeah.
Sir, like these problems in will you ask in exam, sir? like this problem.
Yes. So logical effort definition is input capacitance of logic divided by input capacitance of inverter. What is the condition? That both the inverter and the logic should be designed with this same condition, mu n by mu p. Fine. So what is the input capacitance? So let us take any one input. So let us take A, right? These two A will be connected somewhere in the outside as a single pin in the your IC. So what is the capacitance at this node? As the size is 3, so we can simply write it as 3 Cg. Let's say the gate capacitance, the unit gate capacitance is Cg. So this will have my 3 Cg. Similarly, for NMOS also, I will have 3 Cg. So what is the input capacitance? C input of 3 NAND,
6 Cg.
6 Cg, because these two are in parallel, right? From this node to the ground node. So G or logical effort of 3 input NAND with K equal to 3 is equal to 6 Cg. And what about that of an inverter? Cg, 3 Cg. What is that? Input capacitance of the inverter?
4 Cg.
So the logical effort is 3 by 2. Is it clear?
Can you explain once more, sir?
Sorry?
Can you explain once more, sir?
Okay. Sizing part, have you understood?
Yes, sir.
So if sizing part is clear to you, so let's say this will be your 3 input NAND gate, okay? So let's say this is how it looks like. But whenever you have that packaged chip, let's say this is the sealed package. So you will have one pin, that is your output. You will have one pin, that is your VDD. You will have another pin, that is your ground. You will have one in, it is a 3 input NAND gate, right? So you will
Yes,
have
sir.
one A, you will have another input B, you will have another input C. So you only get to see the outside of the package in real life. You do not get to see what is inside. How many pins you will see? You will see only 6 pins. Is that okay?
Yes, sir.
Now, what is the size of your transistors? These are 3, right?
Yes, sir. It is 3, 7.
So, if a transistor with 1 has a input gate capacitance of Cg, what will be that input gate capacitance with a size 3 of a transistor? What will be this? Yes? What will be this? What is the size of this?
1/2.
So, you remember, right? Last time we had shown this. So, what we are doing basically, now earlier you had a W of 1. Now you have a W of, in the other transistor you have a W of 3. So your capacitance will increase or decrease?
Increase, sir. Increase.
By how much? By the same amount as your W by L is increasing, right?
Yes, sir.
So what will be the capacitance here? If for W by L equal to 1, your capacitance is Cg. For W by L equal to 3, what will be your capacitance? Yeah?
1/3, sir.
Why it is 1 by 3? Again the same thing. You are yourself telling, right? That if increasing W, your capacitance should increase. So now you are increasing your W to 3 times. Why your capacitor will decrease?
Yes, okay, sir.
So
3
in,
CG, sir.
3
yes,
CG.
it will be 3 Cg, right? So earlier you had a capacitor like this. This is your W. So what is the capacitance if this is my Tox? Cg will be what? Epsilon ox divided by Tox times area. Area is your W times L, right? Now
Sir.
what you are doing? Now you are increasing your W to 3 times. Now you have something like this. So what will be the capacitance? Now this entire thing is your 3W. This is your L. What is the capacitance now? What is the capacitance of this? You have to unmute and tell me, otherwise I cannot answer all of your questions. I'll just move on. What is the CG here?
3, sir.
No, not 3. What is CG? Tell me the formula. This is written, right?
1/W by, sorry, Cox by Tox into W by W
Cox
by L.
not, it is epsilon ox. EA by
Epsilon.
D, capacitance is EA by D. This is the very fundamental thing for parallel plate capacitor that you learn in class 9th or 10th grade.
Sir.
So this is the same thing. So Eox by Tox. So this is your 3W times L. So if this is CG, so what will be this one? So are you able to understand why it will be 3 CG? Again, no answer. Okay, I'll just move on. I am not going to take any more question from you because you are not answering.
Yes, sir. Yes, sir.
So basically what is happening at this place, you have a capacitance of 3 Cg. At this place you have a capacitance of 3 Cg. So these two are getting in parallel. So overall in this place you are going to see 6 Cg at the input of your entire gate. So that is what is written here. Similarly, in case of inverter also, on with the same logic, you see 4 Cg. So your logical
Yes,
effort is defined as the input capacitance of the logic divided by the input capacitance of the inverter. That's how you get your 3 by 2. Okay.
yeah. Understood, sir. Understood.
So let us move on. So this is the question that is given. So we'll just see, calculate the delay for 2-input NAND gate which drives 10 2-input NAND gates as shown in figure below. Mu n is 2 times of mu p. That means my k is here 2. Fine. Now can you tell me what do I need to calculate for which transistor, for which 2-input NAND gate they are asking me to calculate the delay?
The first one.
So I need to calculate the delay for this. Fine. We'll see how. So firstly, we'll just quickly calculate logical effort of a 2-input NAND gate with k equals to 2.
Sir,
Yeah.
sir, the answer is 15.33 only, sir. The answer is.
How do you calculate that?
Sir, by some C out by C in, sir. 10 into C in NAND by C in NAND. I have calculated, sir. That's
No, no. Tell me how did you calculate? I need to understand that, right?
okay.
No, no. Tell me how did you calculate? You should have some logic behind the calculation, right? Just by mugging up the formula, if one question you know the formula, you can answer. What about if some different values will be asked in the exam? What will you do? Tell me how did you find out this 15.33?
So first I have taken C in NAND gate, so WP plus WNCG. We have taken 2 input NAND gates, sir. It
You
is
have
4
taken
CG.
2-input NAND gate.
Yes, sir.
So what is that?
It is 4 CG, no, sir.
4
Then
CG is
the
what?
uh,
What is C in and what is 4 CG?
in is the NAND gate in which input is coming, no, sir.
C in is what? You are telling me that C in is 4 CG. How did you get that? And what is your CG?
CG is 3 CG, no, sir. So 3 CG.
You mean to say this is 3 CG?
Yes, sir. Yes, sir.
How did you calculate that? Tell me.
Sir, I taken the formula WP plus WN, sir. The
You should have some. The logical flow of answering that question, right?
Yeah.
So do you have that, or did you get it from somewhere else?
I have got it, sir. I have got it, sir.
So what is the point of studying then if you are getting it from somewhere else?
No, sir. I have done it my own, sir.
So please explain then. Look at your answer copy and tell me.
Okay, sir. Give him a minute, sir.
Yeah, yeah, sure. Meanwhile, we'll just look at how to input NAND gate. So this is your 2-input NAND gate. We'll quickly calculate the logical effort. So let's say this is AB, this is F. So what should be the sizing? What should be the sizing?
All two for the logic and 1 2 for
So this is 2, 2, and this will be 2. This upper 2 is coming from mu n by mu p, and the lower 2 is coming from the series path, right? So what is your C in logic? C in logic is 4 CG. And what is C in logic here?
3 C.
C in inverter is 3 CG. So your logical effort
4 by 3.
is 4 by 3. Okay, now I'll give you some general formula for calculating the delay. So, okay, what is the delay? What is the basic formula that we know? 0.69 times R equivalent times CL plus C internal. Is that clear? C internal is what? C internal of the logic, right?
Yes, sir.
So what we'll do, we'll take C internal of inverter out. So this is something else that we'll define, okay? And we will have CL by C internal inverter plus C internal logic divided by C internal of inverter. Okay. So C internal inverter, we'll define it something, and then we'll take okay, let me just simplify it first. Okay. Okay, this will get complicated if I do it in this fashion. Just let me do it in a fresh page. So I'll have 0.69 times R equivalent times C internal logic times 1 plus CL divided by C internal logic. Fine. Then we will take this times R equivalent times C internal inverter times C internal logic divided by C internal inverter. CL by C in logic divided by C internal logic divided by C in logic. Is this much clear?
Yes, sir.
So this we call it TU, okay, or the unit delay of the inverter. This is just a definition. So I'll write TU times, then I'll multiply this quantity inside. So I have C internal logic divided by C internal inverter plus CL by C in logic times I had C in logic divided by C internal logic, that is this term. Now I will just multiply it with C internal logic divided by C internal inverter. Okay. So now what I have, this I can cancel, right? So now I have TU times C internal. I will tell you why we are doing this, okay? Just for the time being, follow the maths. This is C internal logic by C internal inverter plus CL by C in logic, C in logic by C in I would say inverter times C in inverter divided by C internal inverter. So this is TU. This term we call it as P. Do you recognize this term? What is this term from the last class?
F.
This is F, right?
Electrical
So electrical fan out. What is this term?
gamma.
This is G, right?
G.
Just
Sorry.
now we have seen. And what is this term?
Gamma.
No, gamma was C internal by C in, right? It is gamma inverse. So let us call it C gamma dash. Fine. So this is called unit delay of inverter. This is called parasitic factor. So this P and G are similar. G is the ratio of logic and inverter with respect to the input capacitance. P is the ratio of logic and inverter with respect to the output capacitance. Okay, if we know electrical fan out of logic, G is logical effort, and what is gamma?
Self-loading factor.
Gamma is your self-loading factor of inverter. So what happens basically in real design, VLSI design? So this is and this one. These two are your inverter property, completely inverter property. This has nothing to do with logic, okay? So for any combination, you know that it is very easy to simulate or design the inverters because only two transistors are involved. And logical effort you can calculate with respect to the inverter. Similarly, you can calculate directly with respect to the inverter. That is the relative difference of capacitances from the inverter to the logic. F is something that determines your sizing of the inverter chain, and also it is the only thing that is dependent on the outside world or the load. So if we know the properties of inverter, so we can easily get the overall delay of the logic gate. So the entire purpose is to do this. Otherwise, what is this? Otherwise, you needed to calculate this entire thing, right? For example, R equivalent. So R equivalent, again, you need to calculate for the entire series stuff and this and that. Fine. Similarly, your C internal logic, you need to calculate. CL, you need to calculate. So when you do for billions of transistors, this saves your time. That is why we are doing it in this fashion. Okay. And also in the question, it is asked that calculate the delay. The options are given in delay units. These are nothing but your TUs. So TUs are what? TUs are this is your TU. That is the equivalent delay of the self delay of the inverter, or delay of an inverter if it is unloaded. Delay of an inverter is what? 0.69 times R equivalent times C internal plus CL, right? But in this case, my CL is 0. That means there is no CL present at all. So it is like unloaded inverter delay. Fine. So now from this circuit, let us calculate. So TU, so we have the formula as TP equal to TU times P plus FG gamma dash. So what is G? G we know, TU we do not have to calculate. So we need to calculate gamma dash. What is gamma dash? That is in inverter property. That is your self-loading factor. C internal, that is your C in of inverter, divided by C internal of inverter. In most of the cases, in today's technologies, your gamma dash is 1. This part needs some detailed understanding of the MOSFET capacitances. Okay, why gamma dash is equal to 1. I will take this up in week 13 or in the summary session. I can explain it now, but it will just delay the actual discussion. In summary session, this will be a point that there I will discuss why gamma dash is always equal to 1 mostly. Even in the question, you will also given that your self-loading factor is 1 for the inverter. So gamma dash also we have, G also we have. So we need to F we need to calculate and P we need to calculate. So what is P?
If we have, right, sir? We have it. We have said this electrical fan out is 10, I guess.
So F is equal to, what was F? F was equal to CL by, it was CL by C internal logic, right? C in logic. So so this is the gate. These gates are all same. So this, remember this, if your input gate or the output gate are exactly same, then you can just count the number of lines connected to it. That is what is fan out actually. But in case in the second stage you do not have exactly two input NAND gate, then what? Then you need to calculate this F carefully, right? Do you understand the point?
Yes. Yes, sir. Yes.
So in this case, you have a cheat code that you can directly tell it F is equal to 10. But I'll just, for the sake of completion, what is your C internal? What is your C internal? What is your this C in logic? What is your C in logic? This and this, right? 2CG and 2CG. So C in logic
4,
is 4CG.
4.
So 10 times 4CG. So here you will see 4CG. Here you will see 4CG. Similarly, in all cases, you will see 4CG. So all these 4CG are getting calculated and in parallel, and thus they are getting added. What is C in logic? C in logic is nothing but 4CG. That is this 4CG. So you can get it 10. But remember that if the output stage is different, then you need to calculate this and this. These two may be different. Okay. So that was the point. So F, now you know. What is P? P is defined as what? C internal logic by C internal inverter. C internal logic divided by C internal inverter. So that is the output capacitance. So what is the output capacitance of the inverter? So there you will have one, and in the case of PMOS you will have one. So PMOS you will have CG, and NMOS you will have CG, PMOS you will have 2CG. So it will be again 3CG. What about this? What about the two input NAND gate? I have a capacitance here. 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 So by the way, these are not CGs, these are CDs, because this is at the drain side. So what is this capacitance? This will be 2CD, this will be 2CD, this will be 2CD, this will be 2CD. Now can you tell me, looking at the output node, how many capacitances are connected?
3.
So what is the capacitance, overall capacitance?
6 CD.
So this is 6CD. Okay, this one, and this one all are connected to the F node. One terminal of the capacitance, another terminal of the capacitance is ground. Fine. So that is why it will be 6CD. Three capacitances are in parallel. So this is P is equal to 2.
2.
So now can you calculate this? This is 2 plus F is your 10 times G is your 4 by 3 times gamma is your 1. So this is 46 by 3. That is how your 15.33 is getting evaluated. So yeah, Surya Sakti, tell me, how did you solve it?
So like this method only, sir, I do it.
Did you understood? Have you
Yes,
understood
sir.
what you have
Yes, sir.
done?
Yes, sir. Yes, sir.
You have just understood, or you have understood it earlier?
I understood earlier only.
If that is the case, tell me, if there is, let's say these are all 3 input NAND gates. What will be the answer? All of these are 3 input NAND gates. What will be the answer? Where will you change it?
We have three input NAND gates, sir. We have
Yeah, the output stage is 3 input NAND gate. Where will you change it in the formula? Just tell me what will be your approach. That will be fine. Then I'll understand you have really done it yourself. So you can think out loud. If it is 3 input NAND gate, then what is the first thing you will do? You will size it, right?
yes, sir. I will size it, sir.
So tell me, how you will you size it? Tell me. Why are you keep getting yourself muted? Keep yourself unmuted.
Sir, I am outside, sir. It will get you disturbance, sir.
No, that is fine. We can tolerate with that. You can just tell me what is the sizing of this 3 input NAND gate. What will be the sizing? Anyway, Ankit, can you tell
Three,
me
sir.
what will be 3? So there are 6 transistors, right? Tell me what will be the
Yes, sir.
sizes of the transistors.
Three, sir. The three
Which
transistors, sir.
which one? Which one? NMOS or
Sir,
PMOS?
NMOS, sir. NMOS, sir.
What will be the size of PMOS?
PMOS also three, sir. Three and
No. Ankit, can you tell me what will be the size of the PMOS transistors? So K
It
is
will be
equal
what?
to 2, right? So yeah, Ankit.
So it will be 6, I guess.
No, it will not be 6, right? It will be 2 only. Your
Oh, in the
PDN is 1, PUN will be 2, right? Because that is dependent on K
yes,
only.
yes.
So if that is the case, what is your C in logic? That is your 5 CG in
5
this case.
5
So that 5 CG will replace this 4 CG, right? In the CL, because this is the CL that the main gate is looking at. So all the other formula will remain same, but this part will get 4 CG will be replaced by 5 CG. Is that clear?
Yes, sir. Yes.
Okay. So that is the point. The point of my doing all this detailed analysis is that if the question does not mimic what you have in your assignments or the solutions of the questions that you have, you should be able to attempt for the new questions. Okay, for any combination of question or any combination of logic gates, if you have, and if you have understood what I have told you, then you should be able to do it very quickly, believe me. Fine, so let's move on. So okay, so this is the logic gate chain of logic gates, not inverter. Okay, chain of logic gates. So what will be TP? Let's say this is your stage 1, this is your stage 2, this is your stage 3. So TP will be TP1 plus TP2 plus TP3. So that is what? TU times P plus F times G times gamma dash for first stage, Tu times P plus F plus F times G times gamma dash plus Tu of P plus F G gamma dash. So this is stage 1, this is stage 2, this is stage 3, right? This consideration is same. We have two input NAND gate, so we know all the other things. Fine. So gamma, we know gamma will be 1 for all the logic gates. G is, what is G? Is it an inverter property or is it an it is logical effort, right, of the two input NAND gate. So what is the logical effort of the two input NAND gate? We have just calculated it as 4 by 3, right? So this you know all will be 4 by 3. P is what? P is dependent on what? On the stage itself. It does not depend on the next stage or the previous stage. So the P will also be your 2 in every case, 6 by 3 that we have calculated. Tu is the inverter's delay. So in all cases it will be Tu. So can I write it in this way? It will be 3 times Tu times P plus Tu times G times gamma dash times F1 plus F2 plus F3. Is that okay? Because F or the electrical fan out is the only factor that depends on the load of the logic gate or the next stage input. What is the condition? We know this condition, right? I equals to 1 to 3, f of I should be equal to CL by C in. This is your CL. Do you understand this symbol?
Yes, sir.
So basically what am I telling? F1 times F2 times F3 should be CL is your C, and input capacitance is also mentioned as C. So that is 1. And also from inverter sizing we know that f of j should be equal to f of j minus 1. J belongs to 1 to 3 in this case. So it will be simply f cube equal to 1, or f equal to cube root 1 is equal to 1. Fine. I am writing it in this form so that you can at least try to recall what we have done in last class. So if this is 1 plus 1 plus 1, G is 4 by 3, this is 1. So we have what? T, this is P is 2. So we have 6 TU plus 3 will get cancelled. 4 TU, we will have 10 TU or 10 delay units. Okay.
Yes, sir.
If that you have understood, okay, let me just skip this. I'll do it in next class. So this is so today I'll finish the digital part, and next class we'll look at the analog part. Okay. So this is part of the analog common drain amplifier. Very simple thing. So this question will be the last question for today. So what is the answer? What do we mean by fast operation?
Low propagation delay.
So TP should be lower, right? Fast means TP should be lower. So when will TP be lower? When my R1 is lower,
Yes.
right? So what is my R1?
Del VDS by del ID.
Mu n Cox W by L VGS minus VTH whole square times lambda. R1 inverse is this. Is that okay?
Yes, sir.
So will R1 inverse is generally called as GDS or G out is equal to 2 by is equal to mu n half mu n Cox W by L VGS minus VTH whole square times lambda. And what is your GM? Mu n Cox W by L VGS minus VTH times 1 plus lambda VDS, right?
Yes, sir.
So what is GM by GDS? GM by GDS is, so mu and Cox will get cancelled. 2 will come up. This by this will be VGS minus VTH times 1 plus lambda VDS divided by lambda. So when VGS is equal to VDD, for example, and your VDS is equal to VDD, or at on stage or at off stage, any fashion, you can see that your GM is proportional to GDS. That is proportional to 1 over R on. That is proportional to 1 over TP. Can you see that?
Yes.
So that is why if your GM is higher, your TP will be lower, or it will be faster. Okay. Yeah. Surya Satvik. You have raised a hand. So any reason?
No, sir. No, sir. No, sir.
Okay. So I think that is all what we will do today, and see you next week. Okay. By the way, one important announcement is that so lecture 9 or week 9 will be on next Saturday. Okay. That is 20th. However, week 8 or lecture 10 or week 10 or lecture 10 will be on 22nd. Okay, you will get the notification. It will be 22nd from 6 to 8 p.m. That is on Monday. So I will not be available on 27th. So I will take the session a little prior to that. Okay. Okay. Anyway, I think we can complete
Okay,
if
sir.
others don't have any question, or if you have any question, you can just email me or comment in the YouTube video that what part you did not understand. So I'll make a short video or provide some explanation on it. So Ankit, did you were the person, right, that asked me about that BJT collector profiling, how it is fabricated?
Yes, sir. I asked.
So you have gone through that comment or the content in the comment?
So actually, after that day, I cannot. The link is somehow not working, I guess, because the
Oh,
PDF is
really?
not working from my end. I don't know if it is the problem, but from my end, I have tried once, but it is not working. The link is not
Mm.
opening, I
Okay,
guess.
so what I'll do, I'll just upload wherever you find the this lecture notes, no, that Google Drive link. So I'll
Yes.
upload that extra content on that drive itself so that you can access it.
Okay, sir.
Okay. Okay. Thank you all.
Okay, sir.